Standing waves and normal modes. Part 1. In the earlier module, we considered reflection of waves at one boundary. But there are situations in which reflection takes place at two or more boundaries. Let us understand those scenarios by an example of a string. A string wave going to the right will get reflected at one end, which in turn will travel and get reflected from the other end. This will go on until there is a steady wave pattern set up on the string. Such wave patterns are called standing waves or stationary waves. Now let us understand it mathematically. Consider a wave traveling along the positive direction of x-axis and a reflected wave of the same amplitude and wavelength in the negative direction of x-axis. The equation of the wave will be y1 xt is equal to a sine kx minus omega t plus phi. Let it be equation 1. Wave traveling in the negative direction of x-axis is y2 xt is equal to a sine kx plus omega t plus phi. Let it be equation 2. Putting phi is equal to 0 in equation 1 and 2, we get y1 xt is equal to a sine kx minus omega t, y2 xt is equal to a sine kx plus omega t. The resultant wave on the string is, according to the principle of superposition, y xt is equal to y1 xt plus y2 xt is equal to a sine kx minus omega t plus sine kx plus omega t. Now, using the familiar trigonometric identity, sine a plus b plus sine a minus b is equal to 2 sine a cos b. We get y xt is equal to 2a sine kx cos omega t. Let it be equation 3. Here we note an important difference in the wave pattern described by equation 3 from that described by equation 1 or equation 2. The terms kx and omega t appear separately, not in the combination kx minus omega t. The amplitude of this wave is 2a sine kx. Thus, in this wave pattern, the amplitude is not constant but varies from point to point as a function of sine.